So we're finally moving into the third chapter of this course, that is to introduce you how to integrate a measurable function on a general measure space. The procedure is really similar to what you did in PMATH 450, where you integrate a Lebesgue measurable function. Basically, you take a very specific measure space and you do the integration. If you recall what you did, you start with defining the Lebesgue integral of a positive function by approximating using simple functions, and then you do the other way and you will have a Lebesgue integration for general functions. And we're really doing the same thing here, so the procedure-wise is really the same. You can think about the integrating of a simple function as a Lebesgue version of the Riemann integral. So the simple functions are just like in the Riemann integral, you're dividing a partition and then you use rectangular region on each of the partition. And for simple function, you're really having a rectangular-ish region where the value is constant on each measurable set, and then you have finitely many of them. Okay, so simple functions is easier to define, their integral is easier to define, so that's what we're going to do first. Okay, so in this first lecture of this chapter, we're again defining the integration of positive measurable functions, and in this first video, we're going to define how to integrate positive simple functions. Okay. So here's the setup. So I suppose I have a measure space X, A, and mu, and a simple function is simply a linear combination of some characteristic functions on some chi of AI. Here, AI is measurable in A. And I'm only interested in positive or non-negative functions, so let's assume alpha I is non-negative for now. And now let's define what do I want the integral to be. So let's define a function that's called I of phi. Okay, so eventually I want to show this is the same as the Lebesgue integral, or just the integral of phi. But let's just define it as a function of phi for now. So I define this way. I define it to be the summation of the function value multiplying the measure of its base. Okay, so think about it as the Riemann sum-ish. Okay, so alpha I mu of A is the area of a rectangular region, and then you sum them up. So here AI may not be destroying at all. Okay, so technically this is not a Riemann integral, but we'll see it doesn't really matter. The choice of AI won't matter. So before we move into proving properties of AI, I just want to mention two things. So as you may notice, functions may take mu of these AI may be infinity, but by convention, if I have a 0 multiplied by a mu, which is infinity, I always assume it to be equal to 0, okay? And sometimes we want to have some function that has value infinity on some measure space. If the measure is equal to 0, that's because measure 0 in the Lebesgue integral, measure 0 sets doesn't really matter. So it's infinity or any finite number shouldn't matter. So let's define infinity multiplied by 0 is also 0, okay? The way I define simple function, these alpha I are never infinity, so you won't run into this problem, but let's just make this convention for now. All right, so now let's try to prove the properties of this function I just defined, this I of phi. So here is the list of property I want to prove in this video. So I want to show that I of phi, first of all, is well defined. So whenever you're choosing the I of phi, the definition depend on the choice how you present this phi. Well, you need to show this I of phi is not dependent on how you choose to present this phi. So we need to first of all show it's well defined. Then what I want to show is actually linear. So recall the simple function is a vector space. So I need to show that I of if I have a phi and I have a psi, and then I multiply by a scalar of the psi, then I will have I of phi plus c times I of psi. So this is what I mean by linear. And finally, I want to show it's monotone. Basically, if I have comparison between two simple functions, then I have I of phi is less than or equal to I of psi, okay? So really the first one is the hardest one to prove. The 2 and 3 should follow really easily once we prove this is well defined. So let's prove one. Prove one first. So I want to first of all make a claim that you can assume that this when you write phi equals to summation of alpha I chi of ai, you can replace these ai by disjoint sets. Okay, so I want to can replace ai so that, okay, so first of all, this is a finite collection of ai, and I want to make assumption that these ai actually satisfy the following, so I can assume that ai are actually disjoint, and the union of ai is actually equals to x. Okay, so I want to show that you can always assume phi is presented this way. Okay, so to show that this is really my favorite trick I introduced in the lecture on the simple functions. So you can define, let's say, a of u. So u is a subset of 1 to n. Okay, you let a of u to be everything that's inside u. The intersection of I is in u. And then you intersect whatever the complement, so ai complement if I is not in u. Okay. So these collections, so these AU, they are all disjoint. And their union of these AU, there are 2 to the n of them. So U is a subset of 1 to n. So this will give you the entire set, okay? And moreover, the phi, if you do it this way, you can write it as the following. So you can make it a summation over U, where you have the coefficient becomes summation of I in U of these alpha I, and then you times chi of AU, okay? So first of all, let's show that I of phi defined in one way, defined as alpha I and chi of AI, versus this way where you have chi of AU, they will give you the same I value, okay? So I want to show that these are the same. Well, so how do I show that? Well, in one way, you have the summation of alpha I mu of ai. So this is where what you get by using the first definition. And the other one is basically the summation over all the u. So I should say the first one is summation I going from 1 to n. The second is sum over all the subset of u, where you have the coefficient is I is inside u alpha I, and you multiply the measure of a u, okay? So I want to show that these two are the same, okay? This is my goal, okay? So this is really just very combinatorial proof. So if you start from the right-hand side, you have a double summation, and you can switch the double summation by I sum over any I first, okay? And so here I going from 1 to n. And in the second summation, you need to sum over u, and the requirement is I, this index is part of u, and you sum it up. And you have this alpha I times mu of a u, okay? So alpha I is only depend on I doesn't depend on u, so what you can really say is I sum over all the mu of these AU, and then I multiply everything by alpha I. And you can see that, convince yourself the following, I may put this on your assignment. This AI is just really the union over all U, where I is inside U of these AU, and we see AU are disjoint, so this is really a disjoint union. Okay, so because it's a disjoint union, the sum of this mu of AU will give you the mu of AI, in fact. So this is essentially mu of AI times alpha I, okay? So from there, we show that if you define the I of phi in the first way, is the same as you define I of the phi, well, in the second way, or in the second, if you use the second notation of phi, let me maybe use the red color for the second phi, then you have the same I value, okay? So you can always replace this phi by a linear combination where each of these AU are disjoint and then they union up to the entire set, okay? So now let's try to prove that, well, if you start from two such things, then they actually give you the same I value. Okay, so suppose I have phi is equals to summation of alpha I chi of AI, let's say I going from 1 to n, and suppose it's also equals to summation j going from 1 to m of beta j of chi of bj. And from what we just saw, we can make, without loss of generality, we assume that AI are disjoint, and their union of AI is equal to the entire set. Also, Bj are disjoint, and their union is the entire set as well. Okay, so this is basically what we just saw. We can make this assumption. So I need to show that. So what I need is to show that I of phi doesn't depend on this rearranging of A and B, basically. Okay, so I need to show the following. I need to show that if I define I of phi using the first way, which should give me alpha I of mu of AI, here I going from 1 to n, that should be equal to how we define the second way, the beta j of mu of bj. Okay, so if I can show they are the same, then I'm done. All right, to show that, let's do the following trick. So let's break this AI and bj up. Okay, so because AI and bj, they are partitions of this X, so let's partition each of them even further. So I can do the following. So each of these AI, I can write it as a disjoint union of j going from 1 to m of AI intersect bj. Okay, so I break AI using this partition bj. And this is really a disjoint union because all the b's are disjoint. So because of that, the summation of I going from 1 to n of these alpha I mu of AI, I can break it into summation, a double summation basically. So summation I going from 1 to n, j going from 1 to m of alpha I of mu of AI intersect bj, okay? All right, so we can actually do the same for b as well. So let's just write it down. So summation j going from 1 to m of beta j mu of bj, I can do exactly the same thing. So I do a double summation j going from 1 to m, I going from 1 to n of beta j of mu AI intersect bj. Okay, so I need to show that these two are the same. So that's my goal. Okay, I need to show this is the same. All right, and you can see this is really just a bunch of linear combination, bunch of things multiply mu of AI bj. This is a double summation. So I just need to show that mu of each of these terms are the same. Okay. So why is that? Well, don't forget we have a condition that alpha I chi of AI is equal to summation of beta j chi of bj. Okay, this is our condition. They're both equals to this simple function phi. All right. So if you have AI intersect bj is non-empty, so if AI intersect bj is non-empty, okay, well then I can pick an x inside the intersection AI intersect bj, and if I evaluate phi at this x, okay, again because my choice of AI and bj there are partitioned, they're all disjoint. So because x is inside ai, so it's not inside any other HA, so phi of x is just equals to alpha I times chi of ai x, which is just alpha I. But on the other hand, is also equals to bj because x is inside bj. So because of that, we have when ai and bj have non-empty intersection, then alpha I and bj has to be the same. And from there, we have that alpha I times the mu of ai intersect bj. Well, that's just equals to beta j mu of ai intersect bj. Okay, so that's when ai intersect bj is non-empty. And when ai intersect bj is actually equals to empty set, well, that's the easier case. Well, then alpha I mu of this ai intersect bj, well, mu of the empty set is just 0, so doesn't care what alpha I is, that's just equal to 0. And the same goes for the betas, so mu of ai intersect bj, okay? So in any case, we show that each of these terms, so what we just show, is that if I just fix an I and a J, I have alpha I times mu of AI intersect BJ is the same as the beta J part. Okay, so each term are the same, and I'm doing a double summation, so they have to be the same. Okay, so this proves that they are actually the same. All right, so this proves as well the phi I of phi is well defined. Okay, so I of phi well defined. All right, so now if I want to show it's actually linear, well, this is really simple. So because we proved it is well defined, now we can just pick any representation of this phi, say phi is equal to summation alpha I times chi of ai, and psi is equal to summation of beta j chi of bj. Then a linear combination phi plus c times psi. So here c is non-negative number. So this is essentially have the following representation. So it can be written as summation of alpha I chi of ai plus summation of c times beta j chi of bj. Well, this is just one of many ways of representing this linear combination. But because I of phi is well defined, it doesn't really care how you write this out as long as you write it out as a linear combination of these characteristic functions. So I of phi plus c of psi is just no other than you sum up what you expect to sum up. So alpha I ai plus summation of c times beta j times mu of bj. And this is really I of phi plus c times I of psi. Okay, so linearity is fairly simple. And finally, to show monotone, so if I have phi is less than or equal to psi, and remember we're only dealing with non-negative functions, so let's assume that. Well, then I want to claim that if I take their difference, the psi minus phi is also simple. Okay, so why is that? Well, I am not going into detail, so this is an exercise, but one way to do it is to show that a simple function, a function is simple if and only if its range is finite. Okay, of course, we assume it's measurable. So because the range is finite, well, now I take their difference. The difference is also finite. Okay, so because the range of psi and the range of phi are finite, their difference also has finite range, so it must be simple as well. Okay, so because it's simple, well, clearly you can see that if a function f is positive, if a simple function is positive, then I of f is positive because I'm adding up a bunch of non-negative stuff. Okay, so in particular, I have the I of psi minus phi is positive. And by linearity, this is the difference between I of psi minus I of phi, which is positive. So you can rearrange it and you get your desired inequality. Okay, so the smaller one have a smaller I value. Okay.